Let's plan on, the technology working throughout lecture today. I think I just turned it off, yeah. Well, okay, so the people that I see as not here are Hannah, Sally, and Jaron. All right, we're going to talk about thermodynamics. So, start off with simple things. The first law of thermodynamics. Delta U is equal to Q. Had to go through and change signs from the way I had written this last year, and I forgot to change that one sign. Q minus W, where, right, it was correct with the words on here. Work is the work done by the system. That's what makes it a minus sign. Q is heat added to the system, and U is the internal energy. Now, this being a calculus-based class, we have an interesting thing to note in this equation. U is the internal energy. And so this is delta U, the change in internal energy. But Q is a flow of energy. So it's already a change in energy. Right? Q is how much energy flowed. Likewise, W. So we write this as a calculus equation for what's the difference in using a delta and using a D? A delta is finite and a D is infinitesimal. So we write this in calculus with a du just like normal. But these here, we put a little slash through the D's. Whoa. One of them appeared and one of them did not. Still not a good sign that it took that long to show up. We've been having they put a new Wi-Fi adapter in the room next door because of problems there, and that's caused a cascade of problems in other rooms. Okay, so that's a new way of writing it. That's the calculus way of writing it. And what do those... Yeah, see, told you that was a bad sign. What do those slashes mean? Those slashes tell you that it's not really a derivative, but we're going to do everything with it like it is, or like it's a normal infinitesimal D. So when you see those, all you really need to know is, sure, it means something technical, but for practice, I'm just going to pretend it's a regular D. In fact, many sources will just write as a regular D because that's how we treat it for actual math. Now, talking about the different thermodynamic processes, we're going to calculate the work for each one. So work, force, dot to distance, that integral. For thermodynamics, the force is caused by pressure, so force is pressure times area. And so knowing that, and this one I did get my signs correctly modified, that the direction of the force is going to be outward if I'm doing the work done by the system, then I can put this, my force vector is PA in the plus x direction, where the plus x direction is the outward direction, and then dotted to dx. Well, x hat and dx are in the same direction. And so that dot product is just 1. Because, of course, x hat has a magnitude of 1. So my integral is just integral from a to b of pressure times area dx. But area times dx is dv. So I can make it, my work is integral of pressure dv. Now, we've already seen this, I believe, but just wanted to make sure I covered that at the start. So when we start looking at processes, we can use it correctly. So first, the isochoric process. You should know that isochoric means constant volume. Why is that the first one? Because work was integral of P dV. And so if I have a constant volume process, from V initial to V initial of P dV, that's always going to be equal to 0 because the starting and ending points are the same. That's the V's are the same. So the work is 0 for the isochoric process. very quick to identify that. Now Q, the heat, is equal to the number of moles times the, look, I have here the constant volume molar heat capacity. So just like what we did before, remember we had Q is equal to MC delta T. That was something that applied to solids and liquids. But for a solid or a liquid stays at virtually the same volume regardless of what you do. So that was essentially a constant volume situation we did there. And pressure makes very little difference, so it really didn't matter what the pressure volume were when we did it for the liquid or the solid. But for gas, there's a big difference if you expand it or contract or you change the pressure. So this CV is, well, it's actually defined with the derivative of, Q and T. But the CV is for the case of holding the volume constant. So for an isochoric process where you're holding the volume constant, then that's where we can use it. So Q is equal to NCV delta T. So if I put in, now really technically I should change that to a minus sign, but minus 0 and plus 0 don't matter, so I didn't worry about it. My change in internal energy is equal to the heat plus 0 or minus 0, and the heat is equal to NCV delta T. Now I'm going to go one step beyond this. Notice there's no calculus at this point. Aren't you happy? Yeah, there will be. Going to go one step beyond this. For a monatomic ideal gas, so for monatomic ideal gas, we derived that the average kinetic energy, that's not a K, was equal to 3/2 kT. Which means that the total kinetic energy, which for a monatomic ideal gas means the total internal energy, is equal to the number of molecules times the average kinetic energy of each molecule. So that's going to be 3/2 nKT. Or to match using molar instead of molecule, U is equal to 3/2 lowercase n capital R T. So this is my internal energy for a monatomic ideal gas. Now if I have a monatomic ideal gas, I can say, well, if that's U, then delta U is equal to, in our physics problems, we're not changing n. One of the big differences between we in physics and they in chemistry, they allow n's to change. We don't. We say, why not put it in a box and seal up the box? So, if n stays constant, and r is of course a constant, then the change in internal energy is going to be 3/2 nr delta T. But from our first law equation, I know that's going to be equal to NCV delta T. So what is CV? That's right. All you have to do is match up. There's an N here and an N here, delta T there and a delta T there. What's left on one side is CV. What's left on the other side is 3/2 R. So, we have a way to very quickly determine what that constant volume molar specific heat must be. So I could come back up here and I could say this is equal to N times 3/2 R delta T, because that's what CV is. Of course, it's kind of going around in a circle at that point, but it won't be on the next slide. If you have questions, yeah, Brian.
So that works for any gas?
No, for any monatomic. It worked for any ideal gas on what was printed on the slide. And then what I did below the slide is specific to monatomic ideal gas.
But the exact identity of the atoms doesn't matter because it's a gas. It's helium or hydrogen.
Right. For any gas that fits the, yeah. So, well, hydrogen is a diatomic.
Bad atoms.
Yeah. But helium, neon, argon, krypton.
Okay. Because before we had very heat capacities for different substances with salts.
Right. And now it doesn't matter.
It doesn't matter.
Yeah. Okay, now let's go from isochoric to isobaric. So in the isobaric, we again have a molar specific heat for constant pressure. And like I said, there should be a difference now with the gas because it's very compressible. Now work is identified as the integral of PD. We showed that a few slides back. And so, well, if pressure is constant, that's the integral of a constant dV, which is very simple. That's just going to be the constant times delta V. So the work is very simple, P delta V. Now, where did this come from? Yeah, from the ideal gas law, since PV is equal to nRT, if P is constant, then I can do delta on the left side is equal to delta on the right side, right? The change in PV has to equal the change in nRT. But if P is constant, that becomes P delta V. And N and R are constant, so NR delta T. And so that's how I made the substitution. You do have to pay attention. If pressure wasn't constant, that wouldn't be true. But because pressure is constant, it's true that P delta V is equal to NR delta T.
For an ideal gas.
That's right, for an ideal gas. Everything I'm doing today is at the minimum ideal gas. And then what I'm going to do below the slide will be for a monatomic ideal gas. So here's the relationship from the first law of thermodynamics. Delta U is equal to Q minus P delta V, since P delta V is what work is. Or substituting this term here and this equation here for Q, I can write that as NCP delta T minus NR delta T. Now remember, from monatomic ideal gas, my delta U was 3/2 NR delta T. If I add these, well, actually I won't add them yet. Let's move this side. Why don't we? Sure makes good sense because then we have the CP by itself. And note that we can cancel the N's and we can cancel the delta T's. And so what we'll be left with is CP is equal to 3/2 R plus R is equal to 5/2 R. So the molar specific heat for constant pressure is 5/2 R. What was the molar specific heat for constant volume? 3/2 R. So I'm going to write this. Keep in mind, the CV didn't apply to isobaric, it applied to isochoric. So the two differ by that factor of R. Yes?
A question, and it may not be related, it might just be differences in how people write things. I know for chemistry, most of the time when we're doing normal thermodynamics problems, instead of just using C, we write CP. Is that the same CP as?
Yes, it's going to be the same CP because you're doing it open to the atmosphere.
Okay.
And so it's constant pressure. What I thought you were going to ask, because it's the thing I've been thinking about, is you can still have a capital C or a lowercase c. A capital C would be for your gas, and it would have to have the N's in it. The lowercase c is molar, and you remove the N's. That's what I thought you were going to ask about. You'll see, both things. Okay, so we have isobaric and isochoric, the two easier, going from the easiest to the next easiest. Now we go to the isothermal process. Remember, an isothermal process is a process in which the temperature does not change. So if the temperature doesn't change, then we know that if it's monatomic, so here I've gone straight to monatomic. If it's a monatomic ideal gas, then no change in temperature has to mean no change in internal energy, since internal energy is proportional to temperature. With something else, we haven't established that to be true, although it's still going to, I believe, always be true unless you're changing phase. So the internal energy is going to be constant for this monatomic ideal gas. And so that means my heat minus my work equals 0, right? Delta U is equal to Q minus W, so 0 equals Q minus W, or Q equals W. And then we want to calculate what the work is. Well, I wrote there, work is the integral of P dV from starting to ending. Well, if it's an isothermal process, then I have PV equals nRT is equal to a constant. Since T is constant, nRT is constant, which means PV is constant. So that means that I can replace P with nRT, a constant, divided by volume. So I put that in my integral here. I know I have the entire work done on the right side, but it, to me, makes more sense to go through and show it. I probably shouldn't have had it all shown there, is the truth. So integral from A to B, and for pressure, I'm going to put nRT divided by volume, dV, or a way that's a little more thought-provoking. That's my equation for work. So I do have a little integral. It's a little more interesting integral. It's not absolutely trivial, but I'm sure everyone already knows you don't have to look at an integral table or anything. What's the integral of dV over V? ln V. So this is equal to nRT natural log of the final one over the initial one when you apply your limits. So the work calculation for an isothermal process is a little more interesting, but we can calculate the work if we know the initial and final volumes and the temperature, or of course I could use the initial pressure and volume or the final pressure and volume. I can make lots of substitutions in this. If given the ideal gas law, they're all going to be equivalent. Yes?
So just to be clear then, I guess I was a little confused about this, and especially now that I see it says for an ideal gas. Everything we've talked about today so far has been for an ideal gas.
Yes, everything has been an ideal gas.
Okay.
And in this case, I used monatomic equation simply to show that delta U is going to be 0 if the temperature changes. This equation here is still going to be true even if it's not monatomic. Even if it's not monatomic, the work is still going to be nRT, natural log of V final over V initial, if it's an ideal gas.
Okay. But if it's monatomic, then you're saying which part is specific to the monatomic?
If it's, well, the monatomic I use simply to show that from what we know for the total energy of a monatomic ideal gas, the total energy is linearly proportional to the temperature. So if the temperature doesn't change, the total energy, the internal energy doesn't change. And that relationship is still true even if it's not monatomic, but I was showing the monatomic equation simply because we have an equation we can use to see that. So the generalization is hand-waving. For monatomic, this is, showing exactly why. There's my isothermal, and you might say, wow, he's only 20 minutes in. He only has one process left. What's that one process left? Adiabatic. I might finish early and I might not. The adiabatic process is a process where no heat flows. So that means the first law says change in internal energy is equal to the, well, minus the work. But how do we calculate that work? And to calculate that work, we start with an equation that I am not showing any derivation for. For an adiabatic process, pressure times volume raised to gamma is constant. And what is this power gamma? Gamma is defined as the ratio of the molar specific heat for constant pressure divided by the molar specific heat for constant volume. So for a monatomic ideal gas, that would be 5 R over 3 R is equal to 5/3 If it's not a monatomic ideal gas, then we can't say that gamma is 5/3. You might wonder where this relationship comes from, and the CP and the CV are the keys about telling us where it comes from. It comes from calculating what must happen with the adiabatic process in relation to those CP and CV to get this relationship. So, given that, how do we calculate? Yes, ma'am.
Just confirm the CP and CV for the gases, we have those in terms of number of moles, right? So it'll be like something per mole, right?
They were molar specific heats. So CP was per mole. Okay, how do we find work? What's our starting equation? It's what?
Yeah, cross
minus
yeah, that.
Integral of P dV.
Yeah.
Yeah.
That's what we were getting at.
So I have this relationship. PV to the gamma is constant. What should I do with that equation to allow me to calculate work? Let me write PV to the gamma is equal to P initial, volume initial to the gamma, right? That's what it means for it to be constant. I can relate any two times the values. How can I use that to help me find the work? Yeah, whoops, wrong. That's why, not what you were thinking, because that wouldn't be the way to do it. I want to solve that for P. So there's P, and I'll just plug it in. So plugging that in, what's the integral of this? I'm going to write it one more time to make it as, once again, thought-provoking as possible. Okay, so we're going to have, when we integrate, let's start with the number outside. What do we do when we integrate? We have an exponent. Okay, we bring it down. Well, actually, we divide by the new one. So the exponent goes up by 1, and then we divide by that Yes, sir.
Couldn't we have just taken the ln of that one?
No, it has to be -1. -1 is a very special case. Now things are a little annoying because I have here a v to the minus gamma plus 1. And so if I expand this all out, minus gamma plus 1 is the same as 1 minus gamma. So I'm going to put 1 minus gamma here. I'm going to have 1 over VB to the 1 minus gamma minus that's my equation. We can simplify this. How could we simplify this? What would be your idea for simplifying it? Go ahead.
Because initially, when we have on the top, the exponent was negative, what do we still have being negative on the bottom?
You're right. It should be gamma minus 1. That was, and that's very important to the next step. I was, in my head when I wrote that, I was thinking that's a negative exponent on the bottom. And never did I think that was because I made a mistake. But it was.
Bring them up to the numerator and the reversal sign on your exponent.
Well, these really are negative or they're positive exponents in the denominator because gamma is 5/3. So that's if it was a monatomic ideal gas, gamma is 5/3. And so 5/3 minus 1 is 2/3. So it's in the right position. But what I can do is I can now separate this out as two completely separate terms. Whoops. I used A's where I should have used B's. Okay, now it's not tricky to see what I did. It's a little more tricky to understand why I did it and why it's reasonable. So, Susan, what did I do there?
Just multiply the numerator of the term that's outside the parentheses.
I multiplied it through and I made a change to it. What was the change?
The subscripts.
Yeah, I changed the subscripts because PV to the gamma is constant. I had put P aught V aught, but I could put PA VA or PB VB. As long as I have PV to the gamma, it's still the same value. So I used the same subscript as I had in the denominator. So I brought the numerator through and used the same subscript as in the denominator. Why did I do that? Well, if I have VB to the gamma divided by VB to the gamma minus 1, what am I left with? VB. I put it this way because it makes it so you have a positive in the denominator. And so that is the equation for the work done in an adiabatic process. And of course, I don't think I made any sign errors. I hope not. Yes, ma'am.
So how did the gamma disappear?
When we divide it. Okay, let me show that division. It's just as Chad said. I have VB to the gamma over VB to the gamma minus 1, which could also be written as VB times VB to the gamma minus 1 over VB to the gamma minus 1. Right? If I multiply VB times VB to the gamma minus 1, I add the exponents. So 1 plus gamma minus 1 gives me the gamma. But now we can that those cancel out.
So if you v to the 6 and v to the 5, and you're like, oh, that's just b.
To a sum.
Should we multiply with -1?
Did I multiply by -1?
Yeah,
There's
because you changed the.
Yeah, I changed the denominator. I changed 1 minus gamma to gamma minus 1 when I changed the order on top. So yes, that is, in fact, multiplying top and bottom by -1. Now, when you look at this, go ahead, Chad.
I was just going to say, so the reason that that's not just 0 is because it's not raised to the power of gamma in the final answer there. It's not PAVA gamma, so it's not just.
Oh, right, yes. I was not understanding the question. Now, when you look at this, it seems that it's backward. It really does, right? Because I have the final case, or I have the initial case minus the final case over a positive value. But we know if it's expanding, it should be a positive work. And so if it's expanding, of course, VB is the bigger number, VA is the smaller number. So how is it possible for this to still give me a positive work?
Because we had the change in u is negative w, because it's q minus w. So if it's negative, that's positive, right?
That's not the case here. If we're expanding, the u should go down and the w should be positive. Right, the delta u should be negative and the w should be positive.
What was the question?
How is it possible to have, since we know that VB is bigger than VA, if we're expanding, how is it possible for this to give me a positive value for work?
Pressure.
The pressure is the key here. If the pressure was constant, well, of course, this would be a negative value. But the pressure isn't constant. The pressure A is much lower than the pressure B. I don't have the picture queued up here, but from yesterday's lecture, we had a graph, and on that graph we showed the
Don't you mean pressure B would be lower?
we showed the curve for an isotherm, and then we showed the curve for an adiabat. And for the adiabat, the pressure is dropping more than it does for the isotherm. The pressure really drops a lot. And in fact, from what we have now seen, I gave it to you, we didn't derive it. We know the equation for this. That would be the equation for the pressure on this curve. And so because the pressure is dropping so dramatically, the initial pressure times the initial volume is actually going to be, in this case, the larger value, the final pressure, and the final volume multiplied together is the smaller value. And so it really is doing a positive work when it expands, even though that equation, if you forget that it's multiplied by pressure, you tend to think, well, that's the smaller number minus the bigger number.
So PB is the smaller pressure. Right?
So PB is going to be, yes, the smaller pressure. That's our thermodynamics calculus as far as we're going to go in this class. So I did finish early. But you can see that that last portion was a significant piece of the lecture. What kinds of things then do you have for calculus for the final exam? The final exam, you probably have 2 calculus questions. One that's based on today's lecture. One that is having you calculate the work in one of the various scenarios we did today. The other question will be a calculus question over something we've studied in the previous material. So the stuff that was open game for each of the first 4 exams, that's what the other question will be from. So basically look through the exam reviews for each one, because I think I did exam review for each lecture, and talk about you're going to have this or this. And those are the things for the other calculus-based question on the lecture, or on the exam. Michael?
How long is the final exam? Because I know we have like 2 hours for the final exam instead of the whole lifetime.
Yeah, it'll be the same way. But the questions should be a little easier because I'm covering a broader range, and you can't expect quite as much depth when you have a larger range. At least that's the way I tend to look.
3 hours?
So it'll be the same, like it'll be 10 questions for
Yeah,
11?
yeah.
11 questions.
And
Well, it'll be, I always say somewhere between 10 and 12, just to give myself room. But almost always it's been 10. There are only a few times I've gone away from that. It was 9 for you last time.
But we will only have 2 hours.
Yeah.
and the structure is the same, you have to draw.
Yes. Yeah.
So it will be like 8 questions from like general physics and then 2.
Yes, that's right. Any other questions?
I have a question.
Yes, sir.
Since we all have been coming to calc this whole
Yes.
semester and being diligent, maybe give us a hint on the lab today? As far as, I don't know, I just was having a really hard time when it said to come up with a test out of things in the room. I wasn't sure where to go with that. Like, I don't have a trombone. Which would be cool. You know,
The
I'm just trying to think, because it outlines a procedure that obviously we have all the materials for, and then it said to do our own hypothesis and test outside of that, and I was kind of like, I don't know where to go with this.
do you have the lab guide with you? My answer here has nothing to do with you being good at coming to class each week. It has to do with helping my students.
No.
Okay, so
The
I
little
want
insider tip.
I want to make sure I look at what I require, because I do the same experiments in different classes with different. Each student must select one of 5 different frequencies and record the frequency listed, and record the 2 blanks for each resonance. Okay, so let's say you're a group of 2. Then you have 2 tuning forks that you choose, and you do all of this with. And then you have to have a hypothesis that makes, should relate the sound waves produced by an air column and explained by theory here. So the resonance situation. And you must be able to accomplish the test in the laboratory. So you could bring a trombone if you had one.
Well, see, that might be my observation. Change the length of the tube.
You still need to do the measurements, something where you can do the measurements on it to test it. So you could use that. You could use another tune fork as the thing that you're making a prediction about what, something that's different than what you did here.
Okay. Another tuning fork would be different enough.
Yes. As long as you're not going to repeat the same thing you did with the first 2 tuning forks with the third one and say, aha!
Right.
But, a prediction you could make from your hypothesis that would give you an answer for the other situation. I'll bring in a couple wind instruments if you want. By wind instruments, I mean organ pipes.
Organ pipes?